So I'm Sandra Van Vlierberghe, professor working in the Polymer Chemistry and Biomaterials group at Ghent University. And our job in the DERMA project is to develop wound dressings with added features such as incorporation of antibacterial properties or development of diagnostic dressings. And also we try to develop odor absorbing dressings as well. For the time being, we have been active for about almost 2 years, I would say. And so far, we mainly focused on the polymer development part. And we also explored some preliminary polymer processing techniques to process the dressing. So we start with building blocks, polymer-based building blocks. So giant molecules, which can be adapted by implementing a different chemistry to, for instance, balance the moisture uptake capacity of a dressing, to have a more flexible material or a more brittle one. So we can all tune that by playing around with the chemistry. So on the one hand, the hydrophobicity of the material, biodegradability, for instance, but we can also tune the cross-linking density of a material. And then secondly, an important aspect when focusing on dressing development is the application of processing techniques. And one particular technique that is of relevance for this project is electrospinning. So with this, we actually feed polymer materials in the electrospinning needle. And result is that we can have an electrospin mat with a fiber diameter ranging within the nano up to several micrometers diameter range. And with that, we can make dressings with a high surface area, which also has excellent absorption capacity with respect to the wound environment. Personally, I'm mainly working on elaborating polymer design, so what the people are working on in the lab. So precursors they have to develop and optimize in order to improve cross-linking efficiency, for instance, in the framework of the project. Personally, I also have quite some expertise in the modification of hydrogel building blocks, such as alginate, but also agarose, gelatin, and so on. So during my PhD, I still worked on the functionalization of these building blocks with cross-linkable side groups. And these are essential to ensure that after processing, the structure of the wound dressing will become preserved. So if you apply it on the wound, that the structure will not dissolve. So therefore, you have to introduce covalent crosslinks, so network points, and these then make sure that your wound dressing remains stable. Also, the incorporation of antimicrobial properties I'm quite interested in. So we have worked out approaches which can be used to quantify also the release of the antimicrobial compounds. So there are quite some options that can be explored, but all of them require a dedicated, optimized characterization technique. So we have turned to cyclic voltammetry, but we also looked into the use of XRF and other analysis techniques to really quantify the release of the antimicrobial compound. Because typically, at least you require a release of 3 up to 5 days, and that would already be a substantial advantage compared to the current state of the art, what is used in the clinic. We have some preliminary proof of concept, I would say, on developing core shell fibers, for instance, through co-extrusion electrospinning. So purely conceptually to show that we can indeed encapsulate an active compound inside the core of a fiber. We can encapsulate that with a particular polymer-based material, the shell, which can then also tune the release of the encapsulated compound, what is quite important. So you can play around with the characteristics of your shell to tune the release of the compound from the inner core. So again, if you start to optimize hydrogel cross-linking density with a higher density, the release will be lower. You can also work with complementary chemistry between core and shell to improve the adhesion between the core and the shell. But also I would say that the elaboration of a few analytical techniques to really quantify the amount of antimicrobial compounds released from the system has been a quite important realization of the project, which could also be applicable for other projects working on wound dressing development, because these are actually universal tools which can also be applied to determine release of several antimicrobial compounds, but from whatever dressing. With electrospinning, you actually start off with a polymer solution which is fed from a syringe and which then moves through the nozzle of the needle. At the point of the syringe, you have a voltage. Because of the voltage which is applied between the nozzle and the collector plate, charges are created at the drop of the solution, which comes out of the needle. And at a certain moment, when the surface tension of the drop is overcome, then you start emitting a polymer jet from the Taylor cone. And what happens is that the polymer jet is actually attracted by the oppositely charged collector plate. So typically we put a glass slide like this, or it can also be another collector. We put this onto a metal collector plate, and this is actually the result of the electrospinning process. So during when the jet is collected by the collector plate, the solvent is evaporating. So what ends up on the collector plate are dry fibers. So the solvent is gone. And if we would look with this with an electron microscope, you could clearly distinguish very thin fibers, and you have a random mesh of fibers which could be applied as such onto a wound, or depending on the mechanical properties, which would require a backing to really have a functional dressing. Well, the importance of the project is actually that we want to develop, in addition to, well, there are actually 3 tracks. Let me start with the antimicrobial track. There, the idea is that we want to reduce infections onto a wound with a patient, because it's crucial that the healing time of the wound stays within a particular limited time period. If it goes beyond that time period, there would be a need for surgery. And surgery implies scar formation. So a lot of physical, but also psychological discomfort for the patient in the long term. So if you can reduce bacterial burden and by that reduce the healing process of the wound within this critical time period, surgery can be omitted from the healing process, and scar formation is limited to non-existing in case we have more performant antimicrobial dressings. Secondly, if we look at the odor-absorbing dressings, it's clear that when considering chronic wounds, that odor can be psychologically very painful for patients suffering from chronic wounds. So if we can offer a dressing that captures these odors, I'm sure that patients will have a lot of benefit from this, because they will have the opportunity to also continue with their regular social activities, which they might not do so if they are just concerned about the odor that their chronic wounds produce. And then looking at the third track, so the diagnostic wound dressings, this would actually imply that an infection of a wound would be visualized quite quickly. So actually the patient itself could already see that the wound is infected and either visit the doctor or start applying an antibacterial dressing instead of a regular wound dressing. So again, this would result in faster action of the patient based on a visual observation of an infection. And again, this would lead in a quicker treatment of this infection, so a reduction of the healing time and less scar formation, and no need for additional surgery if the healing process takes too long.